Today we are talking about harvest and conservation. This lecture is based on chapter 32 of the book. Harvest is probably the first operation related to agriculture that was invented. Probably around 3,000–4,000 years before the actual agriculture was invented, humans that were at that point hunter-gatherers were collecting seeds from different grasses, and they used those seeds to produce bread and ale. They also found out that seeds could be stored for long periods as compared to meat obtained by hunting. However, this activity had a very low efficiency, so it probably inspired the invention of agriculture by selecting the best seeds and sowing those seeds every year, and also removing weeds that would compete with the crop. Harvest is the final operation in the agricultural calendar, and our objective by harvesting is to obtain the useful products or materials. In traditional agriculture, the operation of harvesting was based on labor and the partial help of beasts. However, the requirement of labor for harvesting was quite high. For instance, 1 hectare of wheat could require around 130 person-hours for all the operations related to harvesting. That probably limited the arable land surface. See that if we have only 45 days of 10 hours per day available for doing the harvest, one person will be able to harvest 3.5 hectares. That is a very small area as compared to modern agriculture, where with mechanized harvest, one person will be able to harvest 1 hectare of wheat in only 0.4 hours. We can harvest whole plants or parts of the plant, and the moment and the method will depend on the use of the harvested organ. We can distinguish between physiological maturity, which is the time when the biomass of the harvested organs reaches a maximum value, and harvest maturity, which is the optimum date for harvest. This is usually much later than physiological maturity, because in most cases, for agricultural crops, we need to let the crop dry down for the crop having the best water content for storage. Apart from the proper harvest operations, we might require other agricultural operations before harvest. For instance, we might require a preparation of the crop by applying defoliants or promoters of abscission, or prepare the soil either by compacting or applying irrigation or other operations. After harvest, it may be required to apply drying of the the harvest, cleaning, removal of some parts, and sorting according to quality criteria. In this table at the left, we see a classification of harvest operations in terms of the intended use of the harvested organ on the left and the type of harvested organ to the right. According to the use, we can be harvesting for food, either fresh or with transformation, for fodder, in other words, to feed animals, to produce industrial products for the textile, the chemical, the fuel, perfumery and cosmetics or pharmaceutical industries, or we can be producing seeds and propagules for the agricultural sector. In terms of the harvested organ, we might be collecting parts of the shoot that can be vegetative organs or reproductive organs, flowers, fruits, or seeds. And in some special cases, we might be collecting sap, like in maple, latex, like in rubber or opium, or resins, for instance, in pines. In the case of subterranean organs, we might be harvesting roots for beets or carrots, bulbs like onions or garlic, tubercules like potato, or rhizomes like ginger. The type of operation required for harvest will depend on the crop and the harvested organ. For instance, we will use mowing, in other words, cutting, for forage crops and medicinal crops. We will do reaping, threshing, and winnowing for cereals, pulses, and oil crops. For fruits, we will do combing and pulling, and for tubercules and roots, we will apply digging, sieving, and loading. In the case of vegetables, mostly we will apply cutting, and for fruits, for manual harvesting of fruits, we will do gathering. For nuts and olives, we apply shaking, sweeping, and loading. These are the different phases of traditional harvesting of cereals. First, we apply the reaping, in Spanish, the siega. Then, if the crop is not too dry, we leave the harvested plants in the field for further drying for several days. Then the crop is taken off the field, and then we will apply the threshing, in Spanish, trilla. And finally, after threshing, we will separate the grain from the chaff, in other words, the straw, by winnowing, in Spanish, aventado. Here we see some pictures of older practices in harvesting cereals. First, 14th century, reaping wheat. We are cutting, leaving the plants in the field for drying. Here we are seeing one way of winnowing. We will make use of natural wind conditions for separating the chaff from the grain. In some cases, the threshing was performed using flails, in Spanish, mayales, like here, by beating the plants. Or here, this is a tower made for winnowing rice. We let the mixture of grain and chaff fall from a height, so wind will take away the chaff because of its lower density. In general, we can think that there will be yield losses. In other words, that the collected yield will be lower than the actual yield. And these losses might occur before harvest, because of respiration of the harvestable organ, and this is proportional to the water content and temperature. Also, those losses before harvest may be due to the loss of harvestable structures. For instance, the absence of pods, for instance, in the case of rapeseed or legumes, the abscission of fruits, like in fruit trees, the consumption by herbivores, for instance, birds eating sunflower seeds, or the occurrence of fire, hail, or other accidents. We can also have yield losses during the process of harvest. For instance, by the existence of inaccessible parts of the plant. An example would be plant parts that are below the cutter bar when we are collecting a forage. Part of the harvest might be not caught by the harvest system or dropped by it. Sometimes the structures collected might be deteriorated by the harvesting system. In other words, we can produce broken grains or damaged fruits. And in some cases, at the time of harvest, we might reject to harvest parts of the field due to low quality. In that case, part of the yield will be left uncollected. We can also have yield losses after harvest, during packaging, during transport, or more importantly, during storage. The loss of biomass of the harvestable organs, for instance of seeds, will depend on the water content and the temperature. We can also have consumption or deterioration by insects and fungi, and they are also dependent on the water content and the temperature of the product, and more importantly, by the relative humidity in the storage facility. We can also talk about yield losses after harvest when we think about the rejection of part of the harvested product due to quality criteria. In other words, the collected product or a fraction of the collected product may not fit quality criteria, and that means a total loss of the harvest or an additional cost for separating the defective product from the marketable product. Here we see some examples of yield losses. Here we see the case of pigeons feeding on sorghum, the left upper. To the right you see a case of fruit drop in apple before harvesting. In the lower left, we see a picture of wheat plants that were left unharvested, North Dakota in 2019. And in the lower right, we see a picture of Cytophilus granarius, the wheat weevil, in Spanish, gorgojo del trigo, which is one of the main pests affecting grains in storage all around the world. There are some other agricultural operations that are affected by harvest. The date of harvest and the method employed to harvest the crop will be affecting the possible choices for the next crop in the rotation. The method of harvest determines the amount and distribution of residues. And that has implications because for the possible need for additional operations like burning the residues or chopping them or removing or taking them out of the field. Those additional operations will imply a longer time required for land preparation for the next crop. And that limits the possible choices of the species next in the crop rotation. The date of harvest will imply also changes in the irrigation operations. For instance, we need to improve the soil conditions before harvest by irrigating, which will reduce the mechanical resistance of the soil, and that is important before digging subterranean organ harvest, for instance, potatoes. In other cases, we will stop irrigation before harvest to promote abscission and also to prevent soil compaction by the traffic of machinery. This is a case, for instance, if we can also manipulate the soil compaction using tillage, using, for instance, a roller, and that can be a good alternative before harvesting some fruit trees to avoid soil compaction. Pesticide treatments may be prevented before for a period before harvest according to the safety periods marked by the characteristics of the pesticide applied. That may take, for instance, 2-3 weeks before harvest. We will not be able to apply a given pesticide. Considering the case of grains and seeds, we would require for safe storage that the grain is harvested clean, dry, healthy, intact, and if possible, not too hot. This picture shows some silos for storage of grain. However, to obtain dry grains, usually we will tend to delay the harvest date. But the delay in harvest increases dry matter losses from the crop, and in some cases it may also degrade the grain quality. The delay in harvest will also increase seed losses and the risk of deterioration by adverse conditions like lodging of the crop or hail occurrence, the risk of fire, and the risk of production of mycotoxins. Mycotoxins are toxic chemicals produced by natural occurring molds and some pathogens like fusarium. So those are fungi, and the most common type of mycotoxins are aflatoxins, and they are generated by molds of Aspergillus flavus and Aspergillus parasiticus. The risk of contamination with aflatoxins is higher when the harvest of the grain is delayed during wet weather, and also when grain is harvested when it is still wet and the drying of the crop is delayed. In general, water stress increases the susceptibility to the infection by Aspergillus and other molds. It affects cereal grains, but also other products like sunflower seeds, peanuts, cassava, cottonseed, spices, pepper, hay. We see here pictures of Aspergillus flavus on maize and also on peanuts. And in the lower part, we see a map of Europe where the risk of aflatoxin contamination in maize has been calculated using a model that uses meteorological data. It is called AFLA maize. And we see here that the higher risk, which are marked by the dark red colors, the higher risks are occurring in the south of Spain and also in the south of Greece and Italy. And we see also that the risk of aflatoxin contamination in maize is much lower in North Europe. The harvest date of grains and seeds should therefore guarantee seed dry enough. However, if we wait too long, the losses will increase. Therefore, there is a compromise between trying to get dry seeds and also having moderate seed losses before harvest. In many cases, that implies that we will harvest before it is dry enough, and then we will perform drying out of the field. In the case of crops where pod shedding is an important issue, and that occurs, for instance, in rapeseed, on where time is limited for harvesting, farmers apply a two-stage process. First, they perform swathing, which means cutting the crop and leaving it forming windrows where it will dry for a week or a little more. Then, after the crop has dried in the field, in the windrows, we will perform the combining that implies the separation of the seeds from the residues. Here we see a picture of swathing canola in Canada. Canola is synonymous to rapeseed. Here we see the windrows that are being formed by this machine. This is the direction of movement, and these are the windrows that we will leave in the field for a week or a little more. After that period, we will combine the canola, and therefore we will leave the chaff behind and keep only the seeds. The water content of the grain is the main factor to consider for the decision of the time of harvest and to ensure safe storage of the grains. The water content affects the risk of physical damage during harvest, but also the activity of insects and fungi. And more important, the metabolic activity of the seed, which affects the rate of deterioration of the seed in storage, the release of oxygen by respiration, and the heat generation in the stock during storage. In this table, we see that for different water contents, we see the equivalent water potential of the seed from around minus 1.5 megapascal. Remember that this is the water potential equivalent for the permanent wilting point in the soil. That is the point that corresponds to physiological maturity in cereals. And that implies a water content in the seed of a little more than 40%. Between 30 and 40% water content, we have water potentials between 5 and minus 1.5, much lower, of course. Here we are decreasing the water potential. Between 0.2 and 0.3, we will have a high respiration rate in the seeds and also a high activity of biotic factors like bacteria and fungi. So the degradation with that water content of the seed would be fast in storage. Still, between 0.13 and 0.20, the seeds have already a high mechanical resistance, so they will be fit for combined harvesting. But still, the activity of insects and fungi can be high, and the degradation under storage can be fast. Only with lower values between 0.10 and 0.13 of water content, we will have only some activity, a high activity for insects, but the activity of fungi will be small and the degradation under storage will be slow. To determine the optimum water content of the seed, we can use the so-called equilibrium moisture curves that represent the equilibrium between the water content in the seed and the relative humidity of the air around the seed in storage. To do that, we can apply this equation that shows the relationship between the water potential in the seed and the water activity in the air surrounding the seed. In the case of equilibrium, the water potential of the seed will be equal to minus RT divided by M multiplied by the logarithm of the relative humidity. In that equation, S is the molecular weight of water, and R is the gas constant, and T is temperature. So, if we increase the water content of the seed, the relative humidity in the stock will be higher. For any given temperature and relative humidity, the grain will reach the equilibrium moisture content that is defined by this equation, at which water potential in the seed equals water potential of the air around. Here we see two seed moisture isotherms, which are the relationships between seed moisture and relative humidity, for wheat and for sunflower. We see that the moisture isotherms depend on the oil content. So the seed moisture curve for wheat is much higher than that of sunflower. In other words, if we think of a relative humidity of 70% in storage, that corresponds to around 8% seed moisture in the seed of the sunflower and around 13% moisture in seeds of wheat. We can classify the seeds according to their response to drying. We call orthodox seeds to those that can be dried to very low water content without being damaged, and that occurs for most seeds of agricultural species, cereals, legumes, oilseeds, etc. But there are other seeds, not too many species, that are called recalcitrant, where desiccation kills the seed. And that is the case for Quercus species of acorns of the Quercus genus, oil palm, chestnut, and cacao, the lower right picture. Apart from affecting the activity of biotic factors like fungi and insects, the relative humidity affects the loss rate of seed viability in orthodox seeds. And this loss of seed viability increases with relative humidity from 10 to 90%. So if the relative humidity is higher, then the seed viability will be lost sooner. Therefore, we don't want the relative humidity to be very high. And in general, we try to keep it below 67–70% to prevent germination of spores and keeping the loss rate of seed viability under control. The loss of the post-harvest losses in storage have been quantified up to 15% in sub-Saharan Africa. In general, in Western countries, the loss in the storage is much lower than that. In this table, we have summarized the water content or the moisture content of seeds for different points of interest. First, in the first column, we see for each crop the water content at physiological maturity. For instance, for the case of rapeseed, it is 40%. At that point, the biomass of the seeds have reached the maximum value. Okay, but it is too wet to be harvested. For harvesting, rapeseed seeds should have lower than 15%. If we want to harvest the seeds without air drying out of the field, we should. It is recommended to harvest when seed moisture is only 8%, and this 8% value is also the value recommended for long-term storage. Different species have different values of water content at physiological maturity. Also, values of where the seed moisture content is suitable for harvest, and recommended values for harvesting when no air drying is possible or when air drying is going to be applied. The lower values will correspond for long-term storage, and for that usually we will be moving between 8 and 13%, a little higher for cereals. For forages and pastures, we can harvest the crop directly by grazing animals in the field, like in this picture, the upper left, or we can also graze the stubble, the plant residues, after harvest. We see here sheep feeding on wheat stubble. In some crops, the so-called dual-purpose crops, which are some cereals and some rapeseed cultivars, we can allow grazing by the cattle during vegetative growth, as the meristems are not affected. Later, the crop growth can resume, and we will also be able to produce seeds. Forage crops might be harvested and stored as silage when water content is between 50 and 65%. Haylage, which is a type of silage where the moisture content is reduced to between 30 and 50%, or hay, which is the driest type, being between 15 and 25%. In general, the best nutritive quality for forages will be around flowering. So, if we mow later, we will be able to produce a higher biomass, but at the expense of a lower quality. We have also to ensure that the conditions after mowing are dry enough for successful drying of the plants. In the case of silage, the crop is cut green and chopped. Then it is taken to the silo or wrapped in the field and compacted to exclude air. this is important to ensure anaerobic conditions. And those anaerobic conditions will allow the operation of lactic bacteria that will reduce the pH to levels that will not allow the growth of microorganisms. Some crops are left in the field drying for a couple of days before silage starts. In the case of haylage, the crop is left longer in the field before and we let it dry down to between 30 and 50 and then it will be wrapped tightly in plastic covered bales. We see here silage bags to the left. So here this plastic will ensure the anaerobic conditions. And to the right we see the use of silo trenches. So the chopped crop is taken to these trenches, then it is compacted. Here we use a tractor to compact it, and then it is covered by plastic, see the upper right, so the anaerobic conditions are ensured. For hay production, we require a much longer drying period. It can be a week, a couple of weeks. In general, we will try to minimize this period to reduce the respiration losses. The time required to dry the plants before producing the bales, the hay bales, will be proportional to the total biomass, but inversely proportional to the swath area and to the reference evapotranspiration. In hay production, we are running also the risk of mycotoxin production. In general, the process of hay production starts by mowing and sometimes conditioning, which means crushing the plants to speed up drying. Then tedding, which is mixing up and upturning the plants, and then windrowing, piling the plant material in rows to speed up the drying of the plants. And finally, we will produce the baling. Here we see the process of mowing alfalfa and the production of hay bales that can be round or can be square in large square bales or small square bales in the lower right picture. For underground organs that include tubers like potato and yam, roots like sugar beet, turnip or cassava, bulbs like onion and garlic, in general we will try to harvest around physiological maturity when green leaf area is small. In some cases we might sacrifice some biomass and therefore harvest in advance of physiological maturity if we can get much better prices. In general, it is advisable to remove or kill the shoots before harvest, which enhances the periderm thickening of tubers, and that reduces the risk of peeling or bruising during the harvest. In the case of carrots, it is advisable to harvest when the size of the carrot is right for the market. In general, harvesting underground organs requires first cutting the aerial parts, digging the subterranean organ, and lifting that subterranean organ. It is possible then to clean and transfer it directly to a trailer or leave it in the field for some drying. In general, in storage, as opposed to grains or seeds, we need to prevent desiccation. As water loss is proportional to VPD, to vapor pressure deficit, we will reduce this desiccation by applying cool, moist, almost saturated air. Here we see a picture of a complete potato harvester that does the digging, the uplifting, and the cleaning, therefore being able to upload it to the trailer. In the case of fruits and vegetables, we can distinguish between production for the fresh market, which will be collected by hand when the fruits reach the desired size and are close to complete ripening. For wine grapes, the criteria for harvesting is based on quality characteristics like sugar content or color. In the case of olive oil, we can harvest earlier if we want to have higher quality oil, which gets better prices, or later, but if we harvest later, we will have lower prices, but the total oil harvested will be higher. In the case of fruits, we have to consider, in terms of deciding harvest date, the differences between species in the production of ethylene for ripening. Climacteric fruits, which are most important fruits, are climacteric, can ripen off the plant after physiological maturity. So they can be harvested at any time after reaching a size good enough for marketing, and then they can be ripened later. But they can also be harvested when fully ripe, and then the flavor characteristics might improve. In the case of non-climacteric fruits, that includes citrus and strawberries, the fruits have to be on the plant for complete ripening. Therefore, the harvest should be delayed until full ripening. In the case of fruits for processing, and processing might be directed to canning, dried preserves, oil extraction, or juice, the fruits might be mechanically harvested when they are ripe. In the case of nut crops, they will be harvested after physiological maturity, taking into account the water content, which decreases with time. We need to have a low water content to avoid further problems in storage. And also, we want to promote the formation of an abscission zone that will promote the fruit detachment at the time of harvesting. So we need to wait a little after physiological maturity. In the case if we delay harvest too much, then that will increase losses by fruit drop. That might not be a problem in some cases. We see here different alternatives for almond harvesting. In the upper left, we see the kind of traditional way of harvesting by beating the plants to make the fruits drop from the tree. And then we see shakers in the upper right. In the case of an intensive almond harvester, we shake and we use an umbrella to collect the dropped fruits. In the lower left, we see an intensive almond harvester. This is a type of twin machine that goes in both sides of the trees, so they shake the trees and they collect the dropped fruits. In the upper right, we see a super high density harvester in almonds that goes over the trees and then takes all the fruits away. The same goes for olive trees. We see the traditional olive harvest with a man beating the tree and women picking up the fruits from the soil. Then we see an advance by the use of manual shakers that allow shaking of individual branches, which will make the fruits drop. Then an advance would be using a trunk shaker that shakes the trunk of the olive tree and causes the fruit drop. And finally, we see here a super high density olive harvester that will be applied in hedge rows olive orchards.